Good afternoon, everyone. I'm Sharu. I'm a postdoctoral scholar from UCLA. Professor Manu has already talked in detail about the importance of buildability. I'll be talking about a new approach to develop suspensions, thermoresponsive suspensions with a controllable rapid stiffening. So, as you all know, meeting the rheological requirements of a slurry is one of the major issues in major challenge in extrusion-based 3D printing. Since most of you are experts in 3D printing, I'm not going into the details of this. Largely, we can categorize the rheological requirements into a pre-printing and a post-printing rheological requirements. Pre-printing means it should have an optimal yield stress, it should be shear thinning and thixotropic in nature. When we talk about the post-printing requirements is mostly about the post-printing stiffness evolution and how the bottom layers can support the layers that is being printed on top of it. So both this rheological control and the optimal rebuilding kinetics are crucial for a 3D printing structure. Now, coming to more details of this rebuilding kinetics, this slow fluid to solid transition is the central challenge that we have in concrete 3D printing, where this is what impedes the application of concrete 3D printing for building complex geometries. Now, this limits the printing speed, the print height, the maximum possible overhang, and the print fidelity. Now, this slow fluid to solid transition greatly restricts the palette of printable geometries, especially the structures with overhang, and limits the achievable architectures. Now, to utilize the opportunities unlocked by 3D printing and the opportunities unlocked by techniques like topology optimization, we need to have slurries with controllable rapid stiffening. So when we say rapid stiffening, we're talking about stiffening in terms of seconds or minutes. So if we have suspensions with controllable rapid stiffening, we'll be able to achieve higher overhangs, improved print height, improved print fidelity, and improved freestanding length. And those kind of suspensions, we will be able to expand the design and production space that is currently accessible for the concrete 3D printing. We'll be able to print structures which are like lattice structures, which are stretch dominated, topology optimized structures, basically structures with high strength to weight ratio. So today I'm going to show you how we achieve this controllable rapid stiffening in model mineral suspensions. We demonstrated it on suspensions like quartz, which is an inert suspension, calcite, which is one of the most commonly used structural material, and portlandite. Portlandite is a material that we selected because it is an example for high ionic strength and high alkaline suspension. And we also demonstrated it for suspensions which are binary and tertiary mixtures of these minerals. But we can extend this approach to any minerals, including ordinary Portland cement. So how did we do that? First and foremost, we need to have an optimal pre-printing rheology for these suspensions. That means we should have a high solid content and an optimal flowability. So what I've shown here. So what is shown here is an evolution of yield stress as a function of solid volume fraction in the suspension. This is important in suspensions like portlandite. As you can see here, when we cross a volume fraction close to 30%, there's a significant increase in the yield stress and the viscosity of the suspensions. This is basically because portlandite is slightly soluble in water, and because of this, the suspensions are having a high pH and high ionic strength, and this ionic strength is basically screens or the electrostatic charges. So the particles, Portlandite particles, are attractive in nature or slightly weakly repulsive. So what happens is when you put it in water, it get aggregated, and this aggregation limits the maximum volume fraction that we can achieve in these suspensions. So basically, if we use this suspension for printing, we'll be having high drying stresses, high porosity, and mechanically weak structures will be achieving. So having a high solid content and an optimal rheology is crucial. So we need to improve this. So what we did is used for these kind of suspensions where we have high ionic strength and high charge screening behavior, polycarboxylate with a polycarboxylate ether based dispersants are very effective. These dispersant can induce an electrosteric repulsion between these particles, and basically we can mitigate the particle aggregation. With this, we'll be able to reduce the viscosity of the suspensions. We can go from a strongly shear thinning suspensions to an almost Newtonian response by varying the dispersion fraction, and also we'll be able to increase the solid volume fraction in the suspensions from 0.3 to 0.5 without any significant increase in the yield stress or the viscosity. So with this suspension, we'll be able to control both the solid volume fraction and the yield stress independently, yield stress or viscosity independently. So now we have the suspensions which are meeting all the pre-printing rheological requirements. How do we achieve this rapid stiffening? In the last talk, we have seen various methods to improve the stiffening kinetics in Portland-based, in Portland cement-based slurries. Here, we are talking about rapid stiffening. So exclusively depending on the hydration, what will be very challenging because hydration kinetics is relatively slow. So the approach we used is incorporating a secondary binder in the suspension and we can induce rapid stiffening by triggering those secondary binders which is incorporated in the suspension. So how do we induce this rapid stiffening? We induce this by an external stimulus. External stimulus can be thermal, ultrasound, electrical, or electrochemical. We are mainly focusing on thermal and ultrasound triggers. So the rest of my talk, I'll be talking about the thermoresponsive suspensions. We develop thermoresponsive suspensions by incorporating thermosetting resins in the suspension and using heat as the trigger to trigger the rapid stiffening. So when we heat it, these monomers undergo polymerization and induce a gelation in the suspension that induces fluid to solid transition in the suspension. So we can heat these suspensions in a single stage, either in the nozzle or in multi-stage in extruder as well as the heater, or we can heat this immediately after printing, after depositing the layer. So what happens is these suspensions remain flowable until it reaches the activation temperature. There won't be any significant change in the elastic modulus. But once it heated above the activation temperature, the polymerization starts and the polymer network builds up within the suspension matrix. And as the cross-linking proceeds, what happens is this rigid polymer network forms around the mineral particles that induce this rapid fluid to solid transition. Now, the most important part is the selection of these resins and selection of the reaction. The resins that we select should be either soluble or dispersible in water because all the suspensions are water-based suspensions. And another most important thing is it should be stable in highly alkaline medium because ultimately we're going to use this in the cement-based suspensions. So they should be stable in alkaline medium. And coming to the reaction kinetics, they should be thermally latent and should have a good induction period. We don't want to react these resins to react until we trigger it. And once we trigger it, once it reaches the activation temperature, it should have a very rapid reaction kinetics. Then only we'll be achieving that rapid solid fluid to solid transition. And the reaction kinetics should not be affected by the alkalinity of the suspending medium. And in terms of performance, we should have a precise control over the reaction kinetics, the stiffening rate, and the post-cured mechanical strength. So we primarily focused on two reactions: condensation polymerization reaction and the free radical reactions, basically inducing using thermal trigger to induce the gelation within the matrix. So I'm going to the details of one of the thermoresponsive formulation that we developed that is based on amine catalyzed epoxy-thiol click reactions. The reason we chose this reaction because this is having a very high reaction kinetics. And once the reaction is started, it is a highly auto-accelerated reaction once it is initiated. So the epoxy are the resin, the thiol permanent is the cross-linking agent here, and tertiary amine is the initiator or the catalyst. So choosing this initiator is very critical because this is which decides the activation temperature and the reaction kinetics. So the biggest advantage of these formulation is it gives us a lot of controls over the thermal response and the mechanical strength of the printed or the cured composite. So the controls are the resin dosage, thiol to epoxy mixing ratio, the initiator dosage, and the solid loading. So I will show you one example how we can play with these formulation parameters. This shows an DSC thermogram of epoxy-thiol mixtures. Basically, you see two thermograms here, which corresponds to two curing reactions. One is epoxy-thiol reaction, which is happening at the lower temperature here. And another one is the epoxy homopolymerization if you have any excess epoxy in the formulation. So this particular epoxy-thiol reaction is which controls the low temperature rapid stiffening, and this second reaction, the homopolymerization, basically provides the mechanical strength. So by controlling this epoxy to thiol mixing ratio, you will be able to either get a suspension which is having a very high stiffening response, or by using some excess epoxy, you can compromise on the thermoresponsiveness, but you can get a good mechanical strength. And another example for this formulation control, by increasing the amount of initiator in the mixture, we can bring down the activation temperature to whatever temperature that we want, something close to 60 or 50 degrees Celsius. Coming to some results on these mineral suspensions, what you see here is a one-to-one correspondence between the progress of the curing reaction and the stiffening, where the stiffness evolution that we measured using rheometer is and the pure conversion that is procured from the DSC analysis. So as you can see, we get a rapid increase in the elastic modulus once we achieve a threshold pure conversion within the resin. So what is shown here is the real thermoresponsiveness in these suspensions for different suspensions, quartz, calcite, and mixture of quartz and calcite. As you can see, the suspensions, there is essentially no increase in modulus until we reach the activation temperature, and beyond that we see a very rapid increase in the modulus. And there is a stark contrast between the suspension with and without resin. Without resin, there is no noticeable change in the stiffness. And even though depending on the minerals and depending on the volume fraction, we can have difference in the thermoresponsiveness, but still we get an average stiffening rate of 500 Pascal per second, and the activation time can be as low as 30 seconds. A few more examples on the control that we have on the thermoresponsiveness. This shows the effect of resin as a function of weight percentage of the total solids in the suspensions. We can vary this resin content and induce the kind of thermoresponsiveness that we want. This shows the effect of initiator dosage we can bring down the activation temperature. What is shown here is the effect of solid volume fraction and the epoxy-thiol mixing ratio. By using more and more solid content, we'll be able to improve the flexural strength of the suspension. That is obvious. What is interesting here is what is the effect of this epoxy to thiol mixing ratio. By using a mixture which is with excess epoxy, we'll be getting a higher mechanical strength, but we need to compromise on the strain capacity of these suspension, composites. But if we have a more or less stoichiometric ratio of epoxy and thiol, we may be compromising on the flexural strength, but we get a good strain capacity. Yeah. So to conclude, we came up with the design guidelines for these suspensions, where within the printable domain of this formulation, how these various parameters can influence the thermoresponsiveness of these formulations. We have solid volume fraction, resin dosage, the mixing ratio, and initiator dosage. So depending upon the print geometry and the kind of stiffness we want, we can play around with these formulation parameters and control the stiffening response of these suspensions. With that, I conclude here. This is an approach where, which is a facile pathway to overcome the limitations of the current conventional 3D printing, where we can extend this approach to any structural material and which is scalable and economical. And this process has precise control of the formulation parameters to adjust the rheological requirements and the stiffening requirements that we want. Before we conclude, we now working on a radical polymerization-based formulation where we could achieve almost 4 orders of magnitude enhancement in the modulus within less than 30 seconds. So with that, I would like to acknowledge my advisors, Professor Gaurav Sand and Professor Saman Vaishrivastava from UCLA, and our collaborator, Professor Tobin Gadet from Technical University Munich.